So we are continuing with part 2 of chapter 15. And so now in the previous lecture, we did mention that the instrumental variable is one of the way in which you can read the problem of indigeneity. But obviously, we have also realized that it has its own weaknesses, and such that we then have to resort to another method which is better suited for dealing with such problems. And that technique is actually what referred to as the two-stage least squares method. It's more or less similar to the instrumental variable method, but at least the two-stage least square is more intuitive in terms of interpretation. So if you consider the model that appears now on the screen, so you have your model where you have y1 is a function of y2 z1 up until zk. Obviously zk depending on how many um, variables you have to go um, or you need to have in the model. So remember that y2 is your endogenous variable. So now with a two-stage least square, it involves two stages. So the first stage, you estimate or you regress the endogenous variable as a function of all the other exogenous variable. Okay, so once you do that, you then have to create a forecast for that endogenous variable. Now in stage 2, you now have to estimate your original equation. For example, if we have to use the wage equation, remember, so the first instance, so for example, this first equation would be wage as a function of education and all other variables. So now, since if we take education as the endogenous variable, then in the first stage, we have to regress education, and then here on the right hand side, we have to put all other exogenous variable that are supposed to be part of the wage equation. So then we create the forecast for education. Now, once we create the forecast for education, now when we come to the second stage, we can now estimate our wage equation. Obviously, now in this case, now wage will be the dependent variable. Now, what you have here, instead of putting the endogenous variable here like what you would do, you actually have to replace the endogenous variable with the forecast or with its forecast that you created in the first stage. And then obviously the rest of the variables remains as the ones you have in the first stage, because the rest of the variables are basically the exogenous variables that you have. So, and you should also be mindful of the fact that what the method that you are using or that you are applying in the second stage is the OLS that you could actually apply under normal circumstances, even when you do not have the problem of indigeneity. So that is basically how you execute the two-stage least square. Now, obviously, the question comes, if the two methods are similar, then why does the two-stage least square works? Of course, there are a number of reasons. The first one is that when you estimate the endogenous, or when you regress the endogenous variable vis-a-vis all the other exogenous variable, um, remember that on the right-hand side you have all those exogenous variables. So it sort of take away the problem of that problem of indigeneity. And so that is why in the second stage, when you replace the endogenous variable with the forecasted endogenous variable, it is more exogenous, because in the first place, that forecasted endogenous variable is regressed vis-a-vis the exogenous variable. So in a way, it has actually sort of purged some of its endogenous part. And so such that the part which relates to the error term is actually completely eliminated, or to a certain extent minimized. And so then in a situation like that, then you cannot have a problem of endogeneity. Now, what you have to take into consideration is that with the two-stage least square, the standard errors from the OLS in the second stage are wrong, but we can always correct them by using the like the white robust standard error, or any other methods that we can actually use to correct for the standard error. And obviously the two-stage least square can also be used when you have more than one endogenous variable. as well as you can actually also add a lot of other instruments in the model. So that's why it's very useful and more appropriate, or um, um, more appreciated than the usual instrumental variable method on its own. And so that is why you basically, in terms of how to estimate it, actually there are two ways. eViews will actually provide you with two ways. So you can do it manually, where you have to estimate the first stage and the second stage, or you can basically just do it once straightforward, because the eView software package has a built-in technique of two-stage least square, which is actually what is being preferred. So in other words, the manual way of estimating stage one and stage two is not preferred, of course, but because that was the initial way of doing things, it was usually done like that. But now, given the fact that most of the software packages actually have the inbuilt technique of the two-stage least square, you can simply just estimate it once, and you have the output that you require. And we're actually going to see that in the practical or in the eViews video demonstration um, in the video to come. Then lastly, remember that the indigeneity problem has got to do with um, the variance, the error in the variance. Okay, so now, and remember that the problem of indigeneity can also be as a result of maybe a mismeasured variable, or or if you look at the very first slide, I've actually highlighted a number of sources of what could cause the problem of indigeneity. So in most cases, you would still want to use the two-stage least square as a solution, as opposed just to having your normal instrumental variable technique. And that is basically why the two-stage least square is actually more powerful, or tend to be preferred, than the instrumental variable. Of course, we would actually know that under certain assumptions, or under the assumption of completely analogous to the OLS, conditioning of the endogenous variable, or rather than the exogenous variable, the two-stage least square will still remain consistent, and it will also still be asymptotically normal. Okay, and what we should know is that okay, the two of them might obviously be typically less precise. Of course, as I've shown you in terms of the manual one, we do say actually that the second stage standard errors are completely wrong. So it might actually be less precise, obviously, because if there is a problem of multicollinearity, which we know that multicollinearity is nothing else but the exact linear relationship among the regressors. So if you have, again, a problem of multicollinearity, then you would have imprecise estimators. And so that becomes a problem, especially if you are doing it the manual way in the second stage. And then obviously, we also have to correct for heteroscedasticity or serial correlation, analogous, especially if we are using the OLS. Just like the way we correct for heteroscedasticity and serial correlation, we can also still apply it in the two-stage least square, as well as the instrumental variable. We shouldn't forget that the two-stage least square and the instrumental variable, it doesn't only happen in cross-sectional unit or cross-sectional data. It can also happen in time series, as well as in panel data situation. And so that is basically what happens. So it's not exclusive to cross-sectional, but it can cut across all the different type of data set. And then lastly, what we have here is just a parametric way of expressing how to do or how to test for indigeneity. Obviously, the first thing, if you are doing it the manual way, first you have to estimate a reduced form equation. And then secondly, you have now to estimate the whole equation by including the forecasted value from the or including the forecasted variable from the reduced form regression, such that you can then have the two-stage least square applied in two stages, the first stage and the second stage. So reduced form regression is basically estimated in the first stage, and then obviously the second stage you are then having the full equation that you are estimating, so that you can then test for indigeneity. So, and what you have to look out for is the coefficient, the coefficient here, what you have ρ1, because the null hypothesis is that if this is if this coefficient is exogenous, or this variable is exogenous, then it then would actually imply that the ρ1 should be what you call it. So we are basically then saying, if this exhibit the null, or if we have a situation whereby the null hypothesis is that y2 is exogenous, okay, so we can only reject that null hypothesis if this coefficient is different from 0. In other words, if ρ1 is equal to 0, then we cannot reject the null hypothesis of exogeneity. So in order for exogeneity to be pronounced, this coefficient must be equal to 0. But for as long as the coefficient is different from 0, then it actually then means that there is no exogeneity, and so therefore you have a problem of endogeneity within your model, and that's basically how you do this testing for exogeneity. So this ends part 2 of chapter 15.